Hey everyone, and welcome to today's Explainer. We're unpacking a phenomenon today that honestly sounds a bit like science fiction, but it's literally the bedrock of our universe: radioactivity. We're going to strip away the mystery and really dive into the beautifully predictable math hiding behind these seemingly random quantum events. Okay, let's dive into this. Here's the clear roadmap for our Explainer today. 1. The unstable atomic nucleus. 2. The 3 types of decay. 3. The radioactive decay law. 4. Half-lives and measurement. And finally, 5. Real-world applications. All right, Section 1. The unstable atomic nucleus. The battle inside the atom. Think of the nucleus as a microscopic battleground. So, here's a thought for you to ponder. How exactly do you predict the completely unpredictable? Because at an individual level, radioactive decay is entirely random. It's basically a statistical dice roll, and yet physicists have somehow mapped it out with exact mathematical laws. How is that even possible? Well, think about a bag of popcorn in the microwave. You can never predict exactly which individual kernel is going to pop next, right? It's totally random. But if you look at the whole bag, the aggregate whole, you know exactly how long the entire process is going to take. Now, the really fascinating difference here is that while we control popcorn with external heat, you actually can't control radioactive decay by changing the environment at all. It depends entirely on the independent, internal state of the nucleus itself. Because inside that nucleus, there's a constant, microscopic tug-of-war raging between the two strongest forces in nature. On one side, you have the strong nuclear force, trying its best to bind the nucleus together. On the other side, the electrostatic force is violently pushing the positively charged protons apart. And as nuclei get heavier and larger, think uranium or plutonium, that electrostatic repulsion just becomes too much. I mean, holding that much concentrated mass in one tiny space is intensely challenging, and the nucleus just becomes fundamentally unstable. Moving on to Section 2, 3 types of decay, the atom's escape routes. These are essentially the main characters of our story, the different ways an unstable atom tries to finally find some peace. When an unstable atom needs to stabilize, it relies on 3 main escape routes. We've got alpha decay, which ejects a massive helium nucleus, beta decay, which emits much lighter electrons or positrons, and gamma decay, which releases pure, high-energy photons. Let's break down exactly what the atom is throwing overboard in each of these scenarios. Now, what's really interesting about this slide is looking at alpha decay. An unstable parent nucleus like uranium-238 physically ejects an alpha particle, and that's essentially just a helium nucleus. By shedding these 2 protons and 2 neutrons, its mass drops by 4, its atomic number drops by 2, and it literally transforms into a completely different, more stable element, thorium-234. Now, while alpha particles are heavy ionizers, they actually lack penetrating power. A simple sheet of paper or even just human skin can easily stop them in their tracks. Our second route is beta-minus decay. Driven by the weak interaction, a neutron actually transforms into a proton to achieve a better internal balance. It's wild. And to obey the strict universal law of conservation of charge and lepton number, it instantly ejects a high-energy electron, that's our beta particle, along with a tiny antineutrino. So the mass number stays the exact same, but the atomic number actually increases by 1. These beta particles are faster and a bit more penetrating than alpha particles, so you need something like a sheet of aluminum to stop them. And then we have our third form, gamma decay. This one involves no physical change to mass or atomic number at all. Often, right after an alpha or beta decay, the daughter nucleus is left in an agitated, highly excited state. So, to relax down to a stable ground state, it fires off a high-energy photon. This is pure electromagnetic energy, just pure light, not a particle with mass. And because they have no mass and no charge, gamma rays have unbelievable penetrating power. You're going to need thick lead or solid concrete to finally stop them. Section 3. The radioactive decay law, predicting the unpredictable. Think of this math as our ultimate decoder ring for the timeline of the universe's most energetic particles. Okay, so how do we mathematically track all this chaos? Well, looking at the shape of the math here, the total number of radioactive nuclei drops super rapidly at first, when the sample is extremely large, and then it tapers off really slowly over time. This aggregate behavior creates a classic, beautifully predictable exponential curve. Let's move to and see how this builds, logically, through 3 steps. First, our core assumption. The decay rate is directly proportional to the total number of nuclei present, governed by a specific decay constant we call lambda. Second, we use integral calculus to track this over time. And that leads perfectly to step 3, the radioactive decay law itself. This equation allows us to pinpoint the exact remaining number of nuclei at any given moment. But, exponential curves can be kind of tricky to work with intuitively. So physicists reveal this brilliant mathematical trick. By simply plotting the natural logarithm of the remaining nuclei against time, that sweeping curve magically transforms into a perfectly straight line. The slope of that line is simply negative lambda, our decay constant. It literally makes the unpredictable incredibly easy to visualize and manage.
All right, Section 4, half-lives and measurement, ticking atomic clocks. Let's look at how we actually measure the speed of these different decay rates in practice.
To express the speed of these atomic clocks in practical terms, we use something called the half-life. This is simply the exact time it takes for radioactivity to decrease by a factor of 2, meaning half the original nuclei in a sample decay. And the extreme ranges across different isotopes are staggering. Krypton-81M is gone in a flash, with a half-life of just 13 seconds. Technetium-99M takes about 6 hours. But uranium-238? That takes a massive 4.51 billion years just to halve its radioactivity. So the crucial point is, how do we measure the sheer volume of all this activity? Why do both metric and traditional units exist? Well, the metric SI unit is the becquerel, defined as exactly 1 single decay per second. But because 1 decay is such a tiny amount, we frequently use the traditional unit called the curie, which is based on the activity of 1 gram of radium-226. That equates to a massive 37 billion decays per second. Understanding both is absolutely essential for navigating the immense scale of atomic energy. Finally, Section 5, real-world applications, the power of radioactivity. Let's ground all this theoretical physics in everyday reality.
Because we don't just sit back and observe these radioactive forces, we actively harness them. We use targeted alpha and gamma radiation to precisely treat various forms of cancer. We rely on the ionizing power of alpha particles right in our own homes, inside our everyday smoke detectors. And we even use plutonium-238 to provide decades of continuous power for medical pacemakers placed directly inside the human body. This brilliantly illustrates human ingenuity, proving this isn't just abstract science. So, from a microscopic tug-of-war to equations mapping out billions of years, how do these microscopic atomic balancing acts end up powering our modern world? Think about it. The exact same quantum event that is entirely unpredictable for a single atom can be harnessed to predictably save a human life. It's such a profound reminder of the ordered beauty hiding right inside the chaos of nature. Thanks so much for joining me on this explainer, and definitely keep questioning the universe around you.